Here I've shown a planet in two positions, and its velocity at the 2 points is v1 and v2 respectively. And we're imagining here that the planet has journeyed through an angle of azimuth equal to d theta. So I haven't tried to draw this diagram to scale, but imagine that the difference in angle of azimuth is d theta. And we would love to find in this presentation, if we're lucky, an expression for dv d theta. And it'll become clear, I think, as we go through this video, why that's going to be so useful or what it signifies. But first, just to be clear, what do I mean by dv in this case? Well, the answer lies in taking these vectors out of a diagram representing physical space or position space and putting them into vector space, just like we did for the special case of circular orbits. So if we now put them tail to tail, and this is v1, and this is v2, again, the key is you draw them with the same magnitude and relative direction as you would in position space. Now that we're in vector space, well, dv is simply the difference between v1 and v2 when theta approaches 0, or what we might call d theta. Now let's consider the planet Q in orbit around the Sun, and all that we are given as an initial condition is the distance at perihelion. So I've oriented this diagram with the planet here at perihelion in such a way that the angle of azimuth equals 0 degrees. So our reference direction is, again, a ray extending horizontally to the right. And let's make a guess, an incorrect guess, as it will turn out, but let's make a guess as to the shape of the orbit. And let's guess that it's something of an ovoid shape, maybe something like this. And I've drawn it in such a way, as you can see, that the planet at aphelion appears as if it would be right about here. And that furthermore, if you draw a line from where the planet would be at aphelion through the Sun to the position at perihelion, we get a straight line that forms an axis of symmetry. So the top half of the orbit is symmetric with the bottom half. This is an assumption, but it seems to be a reasonable assumption, and it, in any case, will suit our purposes for the sake of discussion at the moment. So here I have drawn in the planet's velocity vector when it is at perihelion, and in keeping with our conventions, I've labeled it v sub 0 because the angle of azimuth at this time is 0 degrees. And we can say something else about this particular velocity vector. In keeping with the conservation of angular momentum, since the planet is now at its closest approach to the Sun, its velocity has to be at a maximum. So we will also call this velocity vector Vmax. Similarly, when the planet is over here at aphelion, furthest from the Sun, the velocity vector at that point is v 180 degrees, but we will also commonly refer to it as Vmin, because the velocity will be at a minimum at this time. Now the next question is, can we say anything about the angle phi that the velocity vector makes or has at perihelion? And we want to claim that phi here must always equal 90 degrees, and that phi over here must also always equal 90 degrees. So let's see the argument for that. So let's say that the velocity vector deviates such that phi equals a little bit more than 90 degrees, let's say 91 degrees. And let's make a triangle here, and I'm going to say that this angle here is 1 degree, even though I've not drawn it that way. But if all of this is true, then this would be 89 degrees, and this would be 90 degrees. And then this displacement vector, dp, is now the hypotenuse of a right triangle, and as such, whatever length this is, the hypotenuse is greater than this distance, L. Therefore, at this point, the planet is no longer, can no longer be considered to be at the closest approach to the sun. So the angle phi cannot be greater than 90 degrees. By the same token, if the velocity vector, let me erase this, was less than 90 degrees, say, again, say this was 89 degrees here, that means that it would have come immediately from a point that was closer to the sun than at the supposed point of perihelion, which is inconsistent with the definition of perihelion. So again, by definition, almost following from the definition of perihelion, the velocity vector has to be 90 degrees at that point. A similar argument can be made to show that the angle phi at aphelion also has to be 90 degrees. So this slide summarizes the relationships between the velocity vectors and the displacement vectors at perihelion and aphelion. And again, the take-home points are that for both Vmax and Vmin, phi equals 90 degrees. And something that goes without saying, really, but just as a reminder, we would also say that for Vmax, alpha equals 90 degrees, and for Vmin, alpha equals 270 degrees. Now recall that we have previously shown that the specific angular momentum, h, of a planet at any point in its orbit is equal to the speed of the planet times its distance from the sun times sine phi. But if phi equals 90 degrees, then sine phi equals 1. Therefore, for our ovoid path, we can say that h simply equals the speed of the planet at perihelion times its distance from the sun at perihelion, and also equals the speed of the planet at aphelion times its distance from the sun at aphelion. Now, we have previously shown that the area swept out by the planet per unit time, dA dt, equals h over 2, which of course, as we've shown, is constant. Now, Feynman's great insight was that if we want to find the general equation for the shape of the orbit, let's say it is an ellipse, for example, we want to get rid of any variables related to time, because the equation for an ellipse is, in a sense, timeless. And he was able to accomplish this by instead finding the change in the area swept out as a function of the change in the angle of azimuth, dA d theta. And he found that is not a constant, but is always equal to 1/2 the distance of the planet from the sun squared. Now, his approach to finding this relationship was a little different than the one I'm going to use, but they're closely related and the results are essentially the same. We begin by using the same line of reasoning that Newton used in proving Kepler's second law. We say that the area swept out by a planet as it passes through an angle theta is approximated by a triangle, as shown here. So we could say that A, the area, equals 1/2 times d1, where d1 is the base, times A, where A is the altitude, and A equals d2 sine theta. And so, again, continuing to use Newton's line of reasoning, if we shrink theta down towards 0, our approximation becomes better and better as we start to reduce further and further this little bit of area that's not included in the area of our triangle. And so as theta approaches 0, a couple of things happen. Number one, d1, the value of the displacement vector d1 approaches that of d2. In other words, they become equal, or essentially equal. And sine theta approaches theta, which, as it approaches the limit of 0, we refer to as d theta. So our formula for the area becomes 1/2 d1 times d2 sine theta, or excuse me, just simply d theta. But since d1 and d2 become equivalent, we can simply write it as, and I'm going to leave out the vector notation here, simply say 1/2 d squared d theta. Or, even better, we can say that for a tiny change in theta, the tiny change in area equals 1/2 d squared d theta, or dA d theta equals 1/2 d squared. But remember, we also know that dV dt equals gm over d squared. We showed that earlier. And now we can combine these two equations and work a little bit more math magic. So we bring this down here, dA d theta, and this down here, whoops, dv dt equals, now we multiply the two right-hand sides of the two equations, 1/2 d squared from here times this, gm over d squared. And right away we can see that the d squareds cancel out. And over here we do a little rearrangement. We trade denominators here, so we say dA dt times dv d theta equals gm over 2. And we substitute for dA dt h over 2, which we've shown before. And rearranging the equation, we can write it as follows. I'm doing this in red because this is pretty important. We can say that dv over d theta equals gm over h. And let's just remember how we got here. It's simply a matter of taking Feynman's discovery that dA d theta equals 1/2 d squared, and we combine that with this formula here, which is essentially or comes directly from Newton's law of gravitation. And by combining those two equations and rearranging, we get this finding, which is going to be very useful. This derivation is so important to our attempt to prove Kepler's first and third law that it's worth taking a moment just to look at it and consider its significance. What it says is this: for any given increment in the angle of azimuth as a planet orbits the sun, the change in velocity is equal to g times m over h. And all three factors on the right-hand side are constants. Therefore, the change in velocity per change in angle of azimuth is a constant, no matter where you are in the orbital path. The other key finding that we discovered in this video is that h, the specific angular momentum, will be equal to the magnitude of Vmax times the magnitude of the distance at perihelion, which will also equal the magnitude of the minimum velocity at aphelion times the magnitude of the distance at aphelion.